Earth grounds in any given area are paralleled with the power company's grounding system. This occurs because the power company connects its grounding system to the Earth in numerous locations, establishing a low-resistance pathway to ground. During an electrical fault, the resulting fault current flows through this grounding system and dissipates into the Earth. The power company gains advantages from this parallel configuration because it aids in diminishing the voltage rise within the grounding system when a fault happens. Elevated voltage levels can endanger individuals and equipment, potentially inflicting harm on electrical devices. Individual installations also reap the rewards of this parallelism, as it mitigates voltage surges within their grounding systems during faults. Such voltage spikes have the potential to compromise electrical components and introduce safety risks. Generally speaking, a greater number of paralleled grounding systems correlates to a reduced voltage surge during a fault. This phenomenon arises because the fault current has the capacity to disperse across a wider region, thereby decreasing the magnitude of current flowing through each independent grounding system. Potential disadvantages exist when paralleling grounding systems. Firstly, if one grounding system sustains damage, it could pose a risk to other systems linked in parallel. Secondly, the likelihood of ground loops may escalate, resulting in noise and interference concerns. Taking everything into account, the advantages of paralleling grounding systems surpass the disadvantages. Nevertheless, it is crucial to recognize potential hazards and adopt strategies to minimize them. Grounding electrode systems, as described in Article 250.50 of the National Electrical Code, aim to create a low-impedance path to Earth. This helps stabilize voltage to Earth during normal operation and limit the voltage rise during electrical faults, providing a path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. The power company's grounding system typically consists of multiple grounding electrodes connected throughout their distribution network. This extensive grounding network provides a very low impedance path to Earth. Individual buildings and facilities also have their own grounding electrode systems, typically consisting of ground rods, ground rings, or connections to metal water pipes. When these individual grounding systems are connected to the power company's grounded neutral conductor, they effectively become paralleled with the power company's grounding system. This parallelism offers several benefits. Firstly, it reduces the overall impedance to Earth, helping to stabilize voltage and limit voltage rise during faults. Secondly, it provides multiple paths for fault current to flow, increasing the reliability of the grounding system. Thirdly, it helps to minimize ground loops, which can cause noise and interference. However, there are also some potential drawbacks to paralleling grounding systems. Firstly, if one grounding system is damaged or disconnected, it can compromise the effectiveness of the entire system. Secondly, paralleling grounding systems can increase the risk of circulating currents, which can cause overheating and energy losses. To mitigate these risks, it is important to ensure that all grounding systems are properly installed and maintained. Grounding electrodes should be sized and installed according to the National Electrical Code requirements. Bonding jumpers should be used to connect all metallic components of the electrical system to the grounding system. Ground fault protection should be provided to minimize the risk of electrical shock and equipment damage. In summary, paralleling grounding systems offer several benefits, including reduced impedance to Earth, increased reliability, and minimized ground loops. However, it is important to be aware of the potential drawbacks and to take steps to mitigate them. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure electrical safety and prevent equipment damage. Article 250 of the NEC covers grounding and bonding. It outlines the requirements for grounding electrode systems, equipment grounding conductors, and bonding jumpers. Grounding electrode systems must be installed at the service entrance and may also be required at other locations, such as separately derived systems. The grounding electrode system must consist of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The grounding electrodes must be connected together to form a grounding electrode conductor, which is then connected to the neutral conductor at the service entrance. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding system. This helps to ensure that the equipment is at the same potential as the earth, reducing the risk of electrical shock. Bonding jumpers are used to connect metallic components of the electrical system together, such as metal conduit, metal enclosures, and metal water pipes. This helps to create a lower impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. The NEC also addresses the issue of ground loops. A ground loop occurs when there are multiple paths for ground current to flow. This can cause noise and interference in electrical systems. To minimize ground loops, the NEC requires that all grounding conductors be connected together at a single point. In addition to the NEC, other standards and guidelines may also apply to grounding and bonding electrical systems. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Electrical and Electronics Engineers, or IEC. It is important to consult all applicable standards and guidelines when designing and installing grounding and bonding systems. Here's a more detailed breakdown of key concepts. Firstly, grounding electrode system. This is the primary connection to earth and consists of one or more grounding electrodes such as ground rods, pipes, plates, or metal water pipes. Its purpose is to provide a low impedance path to earth for fault current and to stabilize voltage to earth. Secondly, equipment grounding conductor. This is a conductor that connects the non-current carrying metal parts of electrical equipment to the grounding electrode system. Its purpose is to provide a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate. Thirdly, bonding jumper. This is a conductor that connects metallic parts of the electrical system together, such as metal conduit, metal enclosures, and metal water pipes. Its purpose is to create a low impedance path for fault current to flow and to minimize voltage differences between different parts of the system. Fourthly, grounded conductor. This is a conductor that is intentionally connected to earth, typically the neutral conductor. Its purpose is to provide a return path for current and to stabilize voltage to earth. Fifthly, ungrounded conductor. These are the conductors that carry the current from the source to the load, typically the phase conductors. Sixthly, overcurrent protective device. This is a device that is designed to protect electrical circuits from overcurrent, such as a circuit breaker or fuse. Its purpose is to interrupt the flow of current when it exceeds a safe level, preventing damage to equipment and reducing the risk of electrical shock. Grounding and bonding are essential for electrical safety and equipment protection. Proper grounding and bonding can prevent electrical shock, minimize equipment damage, and reduce the risk of fire. The National Electrical Code provides detailed requirements for grounding and bonding electrical systems. It is important to consult the NEC and other applicable standards and guidelines when designing and installing grounding and bonding systems. The interaction between parallel grounding systems and the power company's grounding system can be further understood by considering the concept of impedance. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. The impedance of a grounding system is a critical factor in determining its effectiveness. A low impedance grounding system will allow fault current to flow quickly and easily back to the source, allowing overcurrent protective devices to operate and clear the fault. A high impedance grounding system will impede the flow of fault current, which can result in a voltage rise in the grounding system and increase the risk of electrical shock. The power company's grounding system is designed to have a very low impedance. This is achieved by using multiple grounding electrodes connected throughout their distribution network. The paralleling of individual grounding systems with the power company's grounding system helps to further reduce the overall impedance to earth. This is because the parallel combination of multiple impedances is always lower than the lowest individual impedance. In addition to reducing impedance, paralleling grounding systems can also help to improve the reliability of the grounding system. If one grounding system is damaged or disconnected, the other grounding systems will still provide a path for fault current to flow. This redundancy can help to ensure that the grounding system remains effective even in the event of a failure. However, it is important to note that parallel grounding systems can also create some potential problems. One potential problem is the risk of circulating currents. Circulating currents can occur when there are multiple paths for ground current to flow. These currents can cause overheating and energy losses. To minimize the risk of circulating currents, it is important to ensure that all grounding conductors are properly sized and installed. Another potential problem is the risk of ground loops. A ground loop occurs when there are multiple paths for ground current to flow, creating a loop. This can cause noise and interference in electrical systems. To minimize ground loops, it is important to connect all grounding conductors together at a single point. The National Electrical Code provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to minimize the risks associated with parallel grounding systems and to ensure that the grounding system is effective in protecting people and equipment. When considering the impact of parallel grounding systems, it's also crucial to differentiate between different types of grounding. Firstly, system grounding refers to grounding the neutral conductor of the electrical system. This is typically done at the service entrance and at separately derived systems such as generators or transformers. Secondly, equipment grounding refers to grounding the non-current carrying metal parts of electrical equipment. This is done to provide a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate. System grounding helps to stabilize voltage to earth and provides a return path for current. Equipment grounding helps to protect people from electrical shock by providing a low impedance path for fault current to flow back to the source, which will cause the overcurrent protective device to trip and to energize the circuit. The NEC requires that both system grounding and equipment grounding be provided in most electrical systems. The specific requirements for grounding depend on the type of electrical system and the voltage level. In addition to the NEC requirements, other standards and guidelines may also apply to grounding and bonding electrical systems. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Electrotechnical Commission, or IEC. It is important to consult all applicable standards and guidelines when designing and installing grounding and bonding systems. Here are some additional considerations related to parallel grounding systems. Firstly, soil resistivity. The resistivity of the soil is a critical factor in determining the effectiveness of a grounding system. Soil resistivity varies depending on the type of soil, the moisture content, and the temperature. Low soil resistivity is desirable for a good grounding system. Secondly, grounding electrode resistance. The resistance of the grounding electrode to earth should be as low as possible. The NEC recommends that the resistance to ground should not exceed 25 ohms for a single grounding electrode. If the resistance exceeds 25 ohms, an additional grounding electrode should be installed. Thirdly, bonding of metal water pipes. Metal water pipes are often used as grounding electrodes. However, it is important to ensure that the metal water pipes are properly bonded to the grounding system. This is to prevent the metal water pipes from becoming energized in the event of a fault. Fourthly, surge protection. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. SPD should be installed at the service entrance and other locations where sensitive electronic equipment is located. Fifthly, grounding and bonding in hazardous locations. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. Grounding and bonding are especially important in hazardous locations to prevent the accumulation of static electricity which can ignite flammable materials. Parallel grounding systems is a complex topic with many factors to consider. The NEC provides detailed requirements for grounding and bonding electrical systems. It is important to consult the NEC and other applicable standards and guidelines when designing and installing grounding and bonding systems. A common misunderstanding is that grounding alone protects against electrical shock. Grounding provides a path for fault current, allowing the overcurrent protection to trip. It is the bonding that minimizes potential differences which can be hazardous. So, in addition to grounding, proper bonding is crucial for electrical safety. Bonding refers to connecting all metallic parts of an electrical system together to create a low impedance path for fault current. This includes metal conduit, metal enclosures, metal water pipes, and other metallic components. Bonding helps to ensure that all metallic parts of the electrical system are at the same potential, which reduces the risk of electrical shock. The NEC requires that all metallic parts of an electrical system be bonded together. The bonding conductors must be sized according to the NEC requirements. Bonding is just as important as grounding for electrical safety. Here are some common grounding and bonding mistakes to avoid. Firstly, improper grounding electrode installation. Grounding electrodes must be installed according to the NEC requirements. Common mistakes include using undersized grounding electrodes, failing to drive ground rods deep enough into the earth, and failing to properly bond metal water pipes to the grounding system. Secondly, inadequate equipment. Grounding conductors. Grounding conductors must be sized according to the NEC requirements. Common mistakes include using undersized equipment grounding conductors, failing to properly connect equipment grounding conductors to equipment, and failing to provide equipment grounding conductors in all circuits. Thirdly, improper bonding of metal components. Metal components of the electrical system must be properly bonded together. Common mistakes include failing to bond metal conduit, metal enclosures, and metal water pipes to the grounding system. Fourthly, ground loops. Ground loops can cause noise and interference in electrical systems. Common mistakes include creating multiple paths for ground current to flow, failing to connect all grounding conductors together at a single point, and using long grounding conductors. Fifthly, using the neutral conductor as a grounding conductor. The neutral conductor should never be used as a grounding conductor. This can create a dangerous situation where the neutral conductor becomes energized. Grounding and bonding are essential for electrical safety and equipment protection. Avoid these common mistakes to ensure that your electrical system is properly grounded and bonded. The effectiveness of parallel grounding systems also depends on the frequency of the electrical current. At low frequencies, such as the 60 Hz power frequency in North America, the impedance of the grounding system is primarily determined by the resistance of the soil and the grounding electrodes. At high frequencies, such as those associated with lightning strikes or electromagnetic interference, the impedance of the grounding system is also affected by the inductance of the grounding conductors. Inductance is the property of an electrical circuit that opposes changes in current flow. The inductance of a grounding conductor increases with its length and decreases with its cross-sectional area. Therefore, shorter and thicker grounding conductors are more effective at high frequencies. When paralleling grounding systems, it is important to consider the inductance of the grounding conductors. If the grounding conductors are too long or too thin, they can create a high impedance path for high-frequency currents. This can reduce the effectiveness of the grounding system and increase the risk of electrical shock or equipment damage. To minimize the inductance of grounding conductors, it is important to use short, thick conductors and to connect them together at multiple points. It is also important to avoid creating ground loops, which can increase the inductance of the grounding system. In addition to minimizing inductance, it is also important to consider the capacitance of the grounding system. Capacitance is the property of an electrical circuit that stores electrical energy. The capacitance of a grounding system can affect its response to transient voltages, such as those caused by lightning strikes. The capacitance of a grounding system increases with the surface area of the grounding conductors and decreases with the distance between them. Therefore, larger and more closely spaced grounding conductors will have a higher capacitance. When paralleling grounding systems, it is important to consider the capacitance of the grounding conductors. If the grounding conductors have a high capacitance, they can create a resonant circuit that amplifies transient voltages. This can increase the risk of electrical shock or equipment damage. To minimize the capacitance of grounding conductors, it is important to use smaller and more widely spaced conductors and to avoid creating parallel runs of conductors. In summary, the effectiveness of parallel grounding systems depends on a variety of factors, including the resistance of the soil, the size and spacing of the grounding electrodes, and the inductance and capacitance of the grounding conductors. By carefully considering these factors, it is possible to design and install grounding systems that are effective in protecting people and equipment from electrical hazards.